Okay, we learned about classification in general. We learned that one way, actually the best way to classify a point is base classifier. And base classifier basically was computing label given the data point, which depends on class conditional and prior and marginal, but we use some notations to show class conditional and prior. We learned there are three different approaches to classification. One approach is density estimation, and based on density estimation, we can compute this unknown quantities, means class conditional. So we started with this approach with the simple assumption that class conditional is Gaussian. So with the assumption that class conditional is Gaussian, we can derive two methods. One of them is called linear discriminant analysis, and the other one is quadratic discriminant analysis. So our assumption here was that it's a Gaussian function and then we learned that if we want to do classification according to basically Bayes' rule, basically we can compute the posterior for different classes and compare the posterior for different classes. But when you're computing posterior for different classes, the denominator of this ratio would be the same, and you just need to compare class conditional times prior. When it's linear, class conditional times prior would be this quantity times pi k. And if you take a log of this, it's going to be basically, the part that you need to compare would be 1 minus half log of sigma of a class k minus 1/2 x minus mu k transpose sigma k inverse. There's inverse here. X minus mu k. And then there will be times pi k, then you have this term as well. So we call this quantity delta k at point x. So basically you need to compute delta for class 1, delta for class 2, and delta for class k and compare them. Okay? That would be equivalent to do base classifier with the assumption that fk is Gaussian. Class conditional is Gaussian. Then to get some insight about what's happening in LDA and QDA, we decided to consider a special case and see actually what's happening here. This is general for QDA. If it's LDA, then sigma k of all classes would be the same, so you don't need this first term. So this formula will be simplified. So case k was the k that sigma is identity. So when sigma is identity means we have class conditional distribution as spherical Gaussian. So it's completely symmetric and spherical around the mean. In this case, sigma k at point x would be minus 1/2 log of determinant of I minus 1/2 x minus mu k. Then sigma k inverse would be identity x minus mu k plus log of pi k. So this is 0. So when we are comparing different delta for different classes, actually we are comparing this quantity x minus mu k transpose times x minus mu k plus log of pi k. So this quantity, we learned that it is Euclidean, actually a squared Euclidean distance between x and the mean of class k. So for the moment, assume all classes have the same prior. I'm computing delta 1, I'm computing delta 2, I'm computing delta k. And in all of these, I have the first term, which is negative of the Euclidean distance between that point and the mean of class 1. That point and the mean of class 2. That point and the mean of class k. And I'm assuming for the moment that prior is the same for all of these classes. So in comparison, it doesn't matter. Actually, when I'm comparing them, it doesn't matter what the prior is. What is important is just this term. So what's going to happen actually in this case? I have x. I want to classify this x. I want to decide it's in class 1 or in class 2. So I calculate the distance between this point and the mean of class 1. I calculate the distance between this point and the mean of class 2. And according to this quantity, I will assign this point to the class which is closer. Right? So I have two classes. That's mean of class 1. That's mean of class 2. And they're spherical Gaussian. Now you give me one point, x. I want to classify this point according to LDA or according to QDA. But they are Gaussian and prior of classes are the same. So how I'm going to do this? I'm going to compute the Euclidean distance between this point and the mean of class 1. The Euclidean distance between this point and the mean of class 2. Then I'm going to decide that the label of this point is the label of the class that this one is closer to. Right? So basically, linear discriminant analysis or quadratic discriminant analysis, they do a pretty simple job here. You are closer to this class, okay, your label is this. You are closer to that class, to the mean of that class, your label is that. That's as simple as this. Okay? So what about if the prior is not the same? If the prior is not the same, this Euclidean distance is going to be adjusted by the prior. So 30% of the points are here, 70% of the points are here. So the prior of this class is going to be 0.3. The prior of this class is going to be 0.7. So that would be a squared of this Euclidean distance plus log of 0.3, a squared of Euclidean distance plus 0.7. And this will adjust the decision boundary. In a very specific case, I can tell you that if it's LDA and I have two classes with the same prior, decision boundary of LDA would be exactly, a line which is orthogonal to the line which connect mu1 to mu2. That's decision boundary. So any point on this side is closer to this in terms of Euclidean distance. Any point on the other side is closest to this mean according to Euclidean distance. When the prior are the same. When the prior is not the same, it's as if you adjust this point to the right or to the left. So you have more prior here, so this line will be shifted here. Will be shifted that way. So, yeah, Euclidean distance is important, but since you have higher prior here, more likely that points are here. So basically the decision boundary will be adjusted according to the prior. So this, I think, give you a good grasp and intuition of what's happening beyond linear discriminant analysis and quadratic discriminant analysis. So they are pretty simple techniques, and it can be interpreted in terms of computing the distance to the mean of each class as long as the class conditional is spherical. So the covariance is R. Any question here? Okay, what about the case that class conditional is not Gaussian? So that's case 2. And in case 2, which is a more general case, so I cannot assume that sigma k is I. Sigma k could be anything. It's like, the covariance is like a baseball. It's not spherical anymore. So in this case, I can turn this case back to case 1. But how? This sigma, first of all, any matrix can be decomposed using singular value decomposition, right? Like for any matrix X, you can write U S V transpose. Singular value decomposition when U is eigenvectors of X transpose, V is eigenvectors of X transpose X. And these are singular values, a diagonal matrix, right? So I can write singular value decomposition for sigma k, and then it's going to be U S V transpose. Sigma is covariance matrix, it's symmetric. Since it's symmetric, sigma times sigma transpose is the same as sigma transpose times sigma. Right? So this is eigenvectors of sigma times sigma transpose. This is eigenvectors of sigma times sigma transpose. This is eigenvectors of sigma transpose times sigma. But sigma is symmetric, so sigma transpose is the same as sigma transpose sigma. So V is not different from U, in fact. So I can basically write it as U S U transpose. Okay? Okay, now look at this quantity. Look at this quantity. Even I don't need this, this quantity, which was the Euclidean distance. Let me replace singular value decomposition of sigma here. Then it's going to be x minus mu k transpose U S U transpose x minus mu k. Let me take this U transpose inside this bracket and this U inside this bracket. It's going to be U transpose X minus U transpose mu K S U transpose X minus U transpose mu K. Okay. Yes. Thanks. Okay. So I can, this S is basically a diagonal matrix, because we are doing singular value decomposition. It's a diagonal matrix. Yes?
Can there be an inverse on sigma k?
Sorry?
Can there be an inverse on sigma k?
Inverse on?
Sigma k.
Oh, right. So this is basically inverse. Sorry. So what is inverse of sigma k? Let me write this first. So this is sigma. What is sigma k inverse? Sigma k inverse would be U as U transpose inverse, right? Then it's going to be U transpose inverse, S inverse, U inverse. What's U transpose inverse? It's U. Why it's U? Because U is orthonormal matrix, right? U is orthonormal matrix because it's a result of singular value decomposition. It's orthonormal, so the inverse of U transpose basically would be U. Then this S inverse, and it's a diagonal matrix with positive values. So the inverse, S is like this. Lambda 1 to lambda whatever D. Inverse of this would be 1 over lambda D. Okay? And then it's going to be U S inverse U transpose. So basically, when we have sigma inverse here, then it's U S inverse U transpose. So still I can observe this U transpose to this bracket and this U to this bracket. Then it's going to be U transpose X minus U transpose mu K transpose S inverse U transpose X minus U transpose mu K. Okay. Now, this is a diagonal matrix in the form of 1 over lambda 1, 1 over lambda 2, and so on. So I can write it as S to the power of minus 1/2 times S to the power of minus 1/2. And then I can take this S to the power of minus 1/2 inside of each of these brackets. So this quantity basically is going to be S inverse U transpose X S to the power of minus 1/2. U transpose X minus mu K, and take it inside this bracket S minus 1/2 U transpose X minus S minus 1/2 U transpose mu K transpose. Okay. Think of this S to the power of minus 1/2 U transpose as a transformation. Okay, call this transformation, say for example, T. Okay? It's a transformation. or to be, or let me just call u s to the power of minus half t. So this is going to be t transpose. Or if you get confused with t, because both of them are t, let's call it a. This is a transpose. This is a transpose, a transpose, and a transpose. It's as if, I had x, as if I applied a transformation a to x and mapped all of my point to a transpose x. Okay. So if I map all of my points to a transpose x, the mu, which is basically sigma of all of xi's, so each xi has been mapped here. So mu, which is sigma of all of xi's, also would be the mapping of previous mu. So mu actually has been transformed to a transpose mu. So suppose that I have n data point, and then I have a transformation that I apply this transformation to all data points, and it gives me a set of new points. Among this set of new points, there's a new mean, and each point has a transformation. So basically, what I have here is a squared Euclidean distance between transformed point and transformed mean. Right? Because again, this sigma inverse that I had here does not exist anymore. It's like as if it's I. See what happened? I had a case that class conditional was not spherical. So sigma was not identical. I decomposed sigma. I absorbed the decomposition inside the bracket from both sides, and I concluded that it can be written in a form that it's similar to case 1. It's similar to the case that covariance matrix is identical. Okay? So in fact, there is a transformation, and that's the transformation. There is a transformation that can be applied to a non-spherical Gaussian and make it spherical. When you have a Gaussian, which the covariance look like baseball, you can decompose the covariance, find S and find U, and compute U S to the power of minus half, and then apply this transformation to the data. The transformation becomes spherical. Yes?
You mean football instead of baseball?
Sorry?
It's ellipsoid?
Yeah, sorry, football, yeah. You're right. Football, yeah. Because, because would be complicated. It's confusion between soccer and football, Because in my native language, I call, what you call soccer, what's called soccer here is football. So to me, football is spherical, right? So, and I never played baseball, so. Okay, yeah, football. Thanks. That's what I mean. Okay. So any question here? Yes?
So the A transformation takes the ellipsoid and converts back
To spherical, yes. So basically you can turn that case 2 to case 1 in the sense that, in a case that class conditionals are not spherical, you can, there exists a transformation which make it a spherical, and in that space, again, classification means measuring the distance between a point and the mean of a class. Okay? So this gives you an intuition of what LDA and QDA are doing geometrically. And it might be also useful for computation, when you're implementing these techniques, it might be useful. Any question? Okay, so the only other thing that I want to tell you about LDA and QDA is that, so LDA is linear, QDA is quadratic, but there is a way actually to do LDA on a data, but get a quadratic decision boundary, or get a cubic decision boundary, or get a decision boundary of degree 4 and 5, and so on. How can we do this? It's actually a pretty simple trick, When you have a linear function of this form, A is a vector, say for example, as of A1, A2, and X is X1, X2. And B here is a scalar. I just talk about this part. This is a linear function, AX. Suppose that I want to generate a function on the form of bx squared. One way actually to do this is to augment the data and augment the coefficient of the data. Say for example, I have A1, A2 here. I add B1 and B2 here. And when I have x1 and x2, I add x1 squared, x2 squared to this. So if I calculate this multiplication now, it's going to be A1 x1 plus A2 x2. That's the term that I had here. AX plus B1 x1 squared plus B2 x2 squared. As if I have added a term to AX such that it's a quadratic term. It's BX squared. Still, it's linear. My function, let me call this new augmented coefficient C. And call this new augmented coefficient x prime. C transpose x prime is linear. Right? It's just a linear function. But in fact, it is nonlinear on x. It's linear on x prime. It's nonlinear on x because when you compute it on x, it has terms in the form of x1 squared, x1, x2 squared. So it's a very simple trick that you can augment your data the way that you like, and then do LDA, then do any linear method. And then the result would be nonlinear. To do augmentation, I have x, which is d by n. And the first column, say for example, is x11, x12 up to x1d. And this is x21, x22 to x2d, and so on. xn1 to xnd. So to augment the data, I can make x such that it is 2d by n. It's 10d by n, whatever you like. Okay? and keep this part, it's x1, 1 up to x1d, then I'm going to add x11 squared up to x1d squared as the rows of this matrix. I may even want to add cubic terms. I may want to add a function of these, sine of x, cosine of x, whatever you like, And then you have a new matrix x prime when you can compute a linear function on matrix x prime, which is nonlinear on x, because you have augmented your data. Any question? It's sometimes more beneficial to augment the data and compute LDA rather than doing QDA. Just think about the number of parameters that you have to compute in each case. In some cases, more beneficial because the number of parameters are less. Okay, so if you don't have question, I'm done with LDA and QDA. Just let me add something in terms of name. In some texts and some books and some papers, they call what we call LDA, they call it Fisher discriminant analysis. Instead of linear discriminant analysis, they call it Fisher discriminant analysis. What we call Fisher discriminant analysis is a technique for dimensionality reduction that we're going to cover next lecture. So we make this distinction between LDA and FDA, linear discriminant analysis. In our literature of this class, LDA is a technique for classification, but FDA is a technique for dimensionality reduction. In some texts and some books, they exchange these two terms with each other. Sometimes they say FDA and they mean what we call LDA. Was a question somewhere? Yes?
I'm wondering why you would augment the X this way and more rows instead of columns.
So I assume that each row is a feature, each column is a point. So I have n points. I don't add the number of points. I do have n points. I just add features to each point.
Could you also just add, like for the x1 case, you have y1, right? But you can also say like x1 squared, x12 squared, and then add y1, just
No.
add like another data point?
No, you can't. It doesn't make sense, actually. You have n data points and you want to classify them. You can't, make two n data points, right? Yes.
The D is the dimension of features.
Sorry?
The D is the
Dimension of features, right? D is dimensionality of the features, and n is the number of data points. And this is the convention of this class, that we always show our data matrix in this form. When rows are variables or features and columns are data points. Usually, if you look at books written by a statistician, it's the other way around. It's n by d. Books written by machine learning people is this way, d by n. MATLAB is n by d, convention of MATLAB. But it doesn't matter. Any formula that we have, if you take the transpose of that formula, would be the convention of the other part. Okay? Okay, so we are done with LDA and QDA. I told you in the first lecture that we need to cover a little bit of pre-processing techniques. And one important pre-processing technique is principal component analysis. Principal component analysis by nature is not the subject of this class. It's something that we teach in 442, 842 in details. I know some of you have taken 442, 842. I've already sent an email to the class warning that I'm going to the next portion of the class today would be principal component analysis. So since I don't want to see you get bored in the class, if you think that you are completely familiar with PCA, you have seen this in the other lecture or any other lecture, I won't be offended. You can leave the class now. Okay. So principal component analysis, PCA, is a technique for dimensionality reduction. Basically, you can reduce the dimensionality of data using this technique from high dimensional space to lower dimensional space. And this is an example that I usually use. Look at these black points. Dimensionality of these points are 3, right? Because they are in this three-dimensional space. So you can basically specifically tell where these points are just by measuring 3 dimensions, x, y, and z. Okay? So do you agree that dimensionality of these points are 3? Right? So what do you think about dimensionality of points now? 2, right? So with 2 coordinates, I can basically express the position of these points. So the reason that these 3-dimensional points can be expressed with 2 coordinates without losing much information is that these points are on a manifold of this space. So in this 3-dimensional space in this room, there's a manifold such that the intrinsic dimensionality of this manifold is 2. And it turned out that all of these points that we are talking about are on this manifold. So I'm able to find this manifold and unfold it. Then the dimensionality of data is less. Because the intrinsic dimensionality of the manifold was less than the dimensionality of the space. Okay? So PCA actually is a technique which addresses this problem when data is on a subspace. So it's not on a manifold. It is on a subspace. It's completely linear. But the whole data points are in a subspace of lower intrinsic dimensionality compared to the original space. And PCA basically can capture this subspace. Okay? That's one way of looking at PCA. Another way of looking at PCA is to think of PCA as a method which finds the maximum variation of data. Later on, we are going to see that these two basically are identical. If I have some data points, in 2-dimensional space, if they are on a 1-dimensional subspace, or if they are close enough to a 1-dimensional subspace, then I can find this subspace and project these points on this subspace. So I'm going to have a new set of points which are 1-dimensional. Yes?
The points were just random scattered. Like say there was no pattern, would it just be on the subspace?
You can't do that. I mean, if this is the structure of data, you can do PCA. So PCA makes sense if data is on a subspace. But in real world, almost any data set that you are dealing with, set of images, set of documents, text, voice, genes, medical images, and so on, they are on subspaces or submanifolds. So practically, it makes sense to assume that your data is on a subspace. So it's not scattered over the whole space. So one interpretation of PCA is that PCA is a direction of maximum variation of the data. So these points, suppose that I'm looking for a one-dimensional vector in this space, and I want to project all points in this one-dimensional vector. These are my points, right? So one vector that there are infinite number of vectors that I can project these points on them. So that's one vector. If I project all points here, then that would be the variation of the data. I can project these points on this vector, for example. Then that would be the variation of the data. And I can project everything on this one. Then this will be the variation of the data. So one definition of PCA is that PCA, or principal component, the first principal component, is a direction that captures the maximum variation of the data. So basically, that's going to be the first principal component, which I call it U1, or the first principal component. This will capture the maximum. I'm looking for a vector which captures the maximum variation of the data. And then the second principal component would be another vector which is orthogonal to the first one and capture the second maximum variation of the data. And the third one would be orthogonal to these two and take care of the third maximum variation of data. Do you have a question? Okay. So there are different definitions for PCA and different intuitions for PCA. One was in terms of geometry that I explained to you. We are computing a subspace such that all points are on that subspace, are close enough to that subspace. Another interpretation is that we are computing the coordinate of a subspace such that the first coordinate is in the direction of maximum variation, the second is in the direction of second maximum variation, and so on. Okay, there are other properties for PCA as well. So it doesn't matter, you go to compute one of these, then you have PCA and it satisfies all of these properties. But let's go with this one. So among all possible vectors that I can have in this space, I'm looking for the one that captures the maximum variation of the data. So as usual, my setting is that I have n data points. There are d by n. Suppose that I'm looking I'm looking for vector u1 such that it captures the maximum variation of the data, means the variance of u1x is maximum. See, I showed you here the different projection gives you different variance, different variation. I'm looking for the one which gives maximum variation, this one, not this one. This one gives maximum variation, this doesn't. Okay? So I want variance of U1 transpose X to be maximum. So what's the variance of U transpose X? How can I write the variance of U transpose X in terms of the variance or covariance of X? look at a simple case. Suppose that x is just one-dimensional. I have one-dimensional x. If I add a constant to this one-dimensional point, I have n points here. I have n points here, one-dimensional. The mean is mu. If I add a constant to this point, what would be the mean of new points? Sorry? A mu. What about the variance? If it's the variance, what would be the variance of new points? A squared, right? So that's general. When you have a linear transformation of data, the mean will be changed linearly, but the variance will be changed quadratically. Yes? A squared sigma squared. Thanks. From my grade 1 to the end of PhD, I've never been a student because of this problem. I always make mistakes. So be careful. It's possible that when I'm writing on the board, I have typos. And thanks for catching those typos. So, okay. Yeah, it's going to change quadratically. So it's general whenever you have a linear transformation of data, then the mean will change linearly. The variance will change quadratically. Okay? So the mean, if the mean of these data is mu, the mean of new data would be u transpose mu. But what would be the variance of new data? U1 transpose covariance of x, U1. So when this is like sample covariance of x. Great. So this is a scalar now, right? Because we are in one-dimensional space. I projected everything on U1. So everything is one-dimensional. Because, x was d by n. U is d by 1. So U transpose is 1 by d. Then everything would be one-dimensional. So it's 1 by d, d by d, d by 1. So it's going to be a scalar. So this is my variance. And I want to maximize it. So basically, I'm looking for U which maximize this. So this is unknown. So how can I do this? S is known, S covariance of the matrix, but U is unknown. How can I find this unknown matrix vector? Yes. Take derivative and set it to 0. Right. So when you have an optimization problem, you can take derivative and set it to 0. But first, you need to make sure that the problem has a solution. This is quadratic form of this form. It has a mean, but it doesn't have a max. It's unbounded. It can be as large as you like. And intuitively, it's pretty easy to see that. Give me a u and tell me that this u is the solution of this. After taking derivative or whatever, if you give me a u and tell me that u is the solution of this, I will multiply this u by 10. So this will be multiplied by 100. Right? No matter which solution you give to me, I can multiply this vector. You give me this vector, I multiply this vector by a constant. And this vector is going to be larger and larger and make this quantity more and more. So basically, there is no upper bound to this function. This function has no upper bound. You cannot maximize it. So it's ill-defined problem. First, you need to make this problem well-defined. To make this problem well-defined, I need to add a constraint to this problem. A constraint which makes sense. See, I'm looking for vectors, but there is 2 degrees of freedom here. Direction of this vector, length of this vector. I don't care about length, If you tell me that I will project everything on this vector, or everything on this vector, or everything on this vector, it doesn't matter to me. It's the same direction. And what's important for me is this direction. The length is not important to me. So basically, I can add a constraint to this problem. And basically, I can put a constraint on the length of u. So I want to maximize this subject to the constraint that u transpose u is 1. So I'm searching among all vectors with length 1. Okay? Then the only degree of freedom would be direction. So I will go just for the direction of u1. And this 1 is arbitrary. You can set 10, 100, whatever. Just fix it. I'm searching among all vectors with the same length. So you have a constraint optimization problem. How do you tackle this problem now? Yes? Do a Lagrange multiplier, yes. So I will write a Lagrangian, which is based on my prior, and a dual variable lambda, and it's going to be u1 transpose s u1 minus lambda 1 u1 transpose u1 minus 1. Now I need to take derivative of this lambda. Basically, I need to find the saddle point of Lagrangian and set it to 0. When I take derivative of Lagrangian with respect to the primal variable, I have u1 transpose su, and the derivative would be, it's quadratic, right? The derivative would be 2 su. This is a scalar, and the derivative of a scalar with respect to a vector is a vector. Minus lambda, this is quadratic also, and the derivative would be 2u. This is 0. So it means that 2 su1 is 2 lambda u1. And it means that su1 is lambda u1. When u is a vector, lambda is a constant, is a scalar actually, and s is a matrix. So what this equation means? A matrix times a vector is a scalar times the vector. Yes?
Lambda is a singular value?
Sorry?
Lambda is a singular value?
Singular value or?
Eigenvalue.
Eigenvalue. So lambda is eigenvalue of s, and u is eigenvalue of s, right? Basically, this equation tells you that any eigenvector and any eigenvalue of s can satisfy this condition and could be a saddle point of your Lagrangian. So if S is d by d, it has like d eigenvectors and d eigenvalues. All of them, each pair, u1 lambda 1, u2 lambda 2, and so on, satisfy this condition or make the derivative equal to 0. They're saddle point. Which one maximize our objective function among this d? I have d candidate. Which one maximize this? if I do eigen decomposition, I have U1, I have U2, and I have UD. And I have lambda 1, lambda 2, and lambda D. Yes?
Would it be the eigenvector corresponding to the largest eigenvalue?
Eigenvector corresponding to largest eigenvector value. Why is that?
Well, you substitute that, then the max gets scaled by the eigenvalues, so the biggest one will give you the biggest.
The bigger number, right. Good. So any pair satisfy this, but we would like to know which pair actually make this objective function maximum. So here actually I have SU1 be lambda U. So SU1 I can replace SU by lambda U. Right? So when I have UI as UI, it's equal to, I can put SUI, it's UI, SUI, I can put lambda I UI. Lambda is a scalar, so I can write it as lambda I UI transpose UI. But UI transpose UI is 1. So it's lambda I. So it means that U1, if I put U1 in this objective function, the value is going to be lambda 1. If I put U2, the value is going to be lambda 2. And if I put UN, the value is going to be lambda n. And I know lambda 1 is greater than lambda 2, and so on. So if I want the maximum would be this pair. Or the maximum would be basically U1. Okay, U1 is the direction which maximizes the variation. With the same method, with the same token actually, you can prove that the direction of second maximum variation is U2. And the direction of third maximum variation is U3, and so on. Basically, if you want to do principal component analysis, you just need to do eigen decomposition of S and find eigenvectors. Okay? Any question? A simple actually way to implement PCA in practice is to use singular value decomposition. You are given X as your data, it's D by N. Compute the mean of X. So compute X tilde, such X tilde is X minus X bar. X bar is mean of X. Then compute singular value decomposition of X tilde. It's going to be U sigma V transpose. But U is eigenvectors of X tilde transpose, and V is eigenvectors of X tilde transpose X tilde. X tilde transpose is covariance matrix, right? So this is sample covariance matrix. Because you already subtracted the mean, you already have data centralized. So X minus mean times X minus mean transpose is covariance. So basically you can take the mean out, do singular value decomposition, and columns of U would be your principal components. Okay? And it's already ordered. The first column would be the first principal component, second column would be the second principal component, and so on. Okay, there are a couple of things that you would like to do with PCA. One is to map the data to a different dimensional space. So our data is d-dimensional. I want to project the data to p-dimensional space. Okay? So I can do U1 transpose. It's going to be direction of first principal component. I can do U2 transpose. It's going to be direction of second principal component. But I can put U1 and U2 together, and my data is in two-dimensional space, right? So basically, one task is mapping data to p-dimensional space when p is less than d. Okay, in this case, my y is going to be up times x, up transpose times x. When up is the first p columns of U. So in this case, if it's the first p column of U, up is going to be a d by p matrix. I have p columns. So up transpose would be a p by d. And x is d by n. So y would be p by n. So your data will be mapped to p-dimensional space. If it is 1, then it's going to be just projection on the first principal component. But if it's 1 and 2, it's going to be projection on the first two principal components. Okay, that's one thing. You want to map the data to p-dimensional space. That's what you do. Sometimes it's useful to reconstruct the data. Means you project the data in lower dimensional space, you want to project it back to the original space. So y was U transpose x. So I projected the data using the transformation U, and U is orthonormal. I mean, U is in fact the inverse of U transpose. So U transpose project the data to low dimensional space. If I multiply everything by U, I will take it back to the original space. So basically, x hat would be U times y, or U transpose x. When I write U here, actually, in most cases, I mean UP, U is d by d. But usually you truncate it and keep the first p dimensions, okay? So even if I don't write p here, that's what usually you do. I write it in general form because it's true for d by d matrix as well. But what usually is going to be useful is to use only p dimensions, go to p-dimensional space and use p-dimensional p first column of U and take it back to the original space. X hat here has the same dimensionality as x. It's d by n. But it's reconstructed based on the first p principal component. So basically, if I have d principal component take care of the whole variation of the data. The first one is the maximum variation. The second one is the second maximum variation, and so on. Suppose that I map everything in the first two principal components. Then I take it back. It is in the same dimension of the original data, but has been reconstructed only based on the first and second direction of variation. It doesn't have anything to do with the third direction of variation. I will show you demo and example later on to make it more clear. But this is another task that you want to do, reconstruction. And then you may want to sample, basically you want to map the out-of-sample data and reconstruct out-of-sample data. But let me use this 10 minutes time, I will explain this later, to show you okay, I just load a data set here. And this data set will be in a matrix X. The size of matrix X is 560 by 1965. So I have data points on dimensionality of 560, and I have 1965 of them. Okay, it's in D by N matrix. So the column of these matrices are images. So any of these vectors of length 560 is an image of resolution of 2 by 28. So 2 by 28 is 560. So basically I can take one image, for example, the first image of X, and I can reshape it to a matrix of 2 by 28, and then I can just visualize it. So believe it or not, it is a face. It is just, I need to transpose it. And let me show you this. Do you see it? Do you see the face here? There's a face here actually, but it's noisy. You know, I added some noise to this face, so that was column 1. Let me show you another column of this matrix. It's another face. So, and we have close to 2,000 of these faces. These are noisy. Okay, the covariance matrix would be 560 by 560. If I decompose it, I have, if it's full rank, I have 560 principal components, right? So there is 560 direction of variations. If I project the data on the first principal component, it will capture the maximum variation of the data. What does it mean? You know, these faces are different because actually all of them are the face of the same person. But they're different because of different reasons. Because this person has different face expression. In some of them, he's happy. In some of them, he's sad. It's different because he has different views. Some of them are right views, left views, different sidal views. They are different because of different reasons. So there are different directional variations to this data. If I project everything on the first principal component, it will capture the maximum variation of the data. If the maximum variation of the data has to do with being happy or sad, or being in different views or different colors, it will be captured. And the second principal component would be the second variation of the data, and I have 560 of them. Okay? When I project it back to the original space, I can reconstruct the data, but I can reconstruct the data according to the first 10 principal component, the first 20 principal component. Okay? Not all of them. Means that I can capture the first 20, the first 10, the first 5 principal component, the first direction of variations, and get rid of the rest. So one reason that these points, these images are different is that they have different noise. Do you think noise would be among the first couple of principal components or not? No. Because if noise was among the first principal component directions, you are not able to see a face behind this image. You can see a face because noise is not dominant. If noise was dominant, you were not even able to see that there is a face behind it. Okay, what I'm going to do is I'm going to do singular value decomposition. Because we learned that we can do PCA by singular value decomposition, then what I have in U is the first principal components. So size of U is 560 by 560, so I have 560 principal components. So among all of these principal components, if I take, say, the first 10 principal components and multiply this by x, then I have lower dimensional representation of the data in 10-dimensional space. But I can reconstruct the data by multiplying everything, by multiplying y by u. I can go to lower dimensional space here, but I can reconstruct it if I multiply u transpose x by u. So if I compute, I can call x hat to be u, x hat to be u times basically, sir, it's u everything but the first 10 principal components times everything in the first 10 principal component transpose times x. What does it do? It does take the data to p-dimensional space, but then it takes it back and make x hat, which has the same dimensionality of x, but it has been reconstructed only based on the first 10 principal components. So if you look at the size of x hat, the size of x hat is the same of x, but among 500, yes.
Is your P 10?
Yes.
Do you have any reason for choosing P to be 10?
No.
So you just chose
I just said 10. Could be 20, anything. I chose P to be 10. So I can get back to the original, the dimensionality of the original space. So Okay, what I have in the top is image number 1030 in X. Okay, let's look at image 1030 in X hat. See what happened? That's the same image, but you don't have noise anymore. Why don't we have noise? Because noise was not among the first 10 principal components, right? So I projected everything in 10-dimensional space. I reconstructed. So when I reconstructed, there hasn't been any noise because noise is not one of the main principal, one of the main direction of variation. So it's noiseless, right? So let me show you another image, for example, here. That's image number 12. And this is x hat of 12. Okay? Yes?
In this case, did you know that the first 10 didn't capture the noise? Like, what if, like, how do you know which principal components don't include noise? Or will it always be the case that the ones that maximize the variance will leave out the noise?
No.
Or
I'm pretty sure that the noise is not among the first principal component because I can see sort of phase here. Noise is not dominant. But P, optimal P is 10 or is 20 or is 50 or is 200, I don't know. And ask this question at the beginning of next lecture because we're over time, and I will tell you how you can compute the optimum P.